Happy Thursday, dreary Thursday. And last official meeting day. Feels like yesterday that we just started. Moment you've all been waiting for. Final exam. Bless you. 10 questions. That covers everything we've done in this semester in no particular order. And not necessarily evenly distributed. It was left up to the RNG gods. It should go without saying, make sure you complete all of your work legibly. If I'm unable to read your work, it's not getting graded. Obviously, you have to show all of your work. Right? Need more room, you're allowed to use the back. And I did print it single-sided. Just make sure you clearly note on the problem that you're continuing your work on the back and make sure you label that work. Or you can use scratch paper, right? Separate loose leaf paper. Again, just leave a note that you're continuing the work on said loose leaf paper and clearly label that work. Attach all of the loose leaf paper at the very end. Notes, textbook, special course materials, unless I specifically say you're not allowed to use it. Can't discuss this with anyone but me. It will be due by the end of our final exam period, which is May 4th, 10:15 to 12:15. So I will be in this room that entire period. And if you want, you can come in during that period to sit down and finish it up. You shouldn't need to attach any kind of graphs or anything. So if you want to look at a graph, be my guest, but you don't actually need to include it. Fairly straightforward. I had a lot of fun writing up this exam and writing up the solutions. So I want that vector decomposed into its components with respect to B. I can't say any more than that because that is something that we did go over, and that's what I'm testing you on. That was way back at the beginning. And of course, most importantly of all, as always, have fun. Don't you shake your head. If you're not having fun, then you're doing something wrong. No, but you will fail if you don't have fun. We're going to finish up the last two problems. I think we're kind of halfway through one of them. All right, so remember, we're trying to find circulation using Stokes' theorem. So we found the curl already of the vector field. We parametrized the surface, found its normal vector, and the parameter domain. And we said the curl 0, 0, negative 3x squared y squared. Right, double integral of the domain, we have to evaluate now that curl over the parameterization. And what was the parameterization? It was 4 times S1. So 4 squared is 16, 16 squared, 256. 2 to the 4th squared, 2 to the 8th, yeah, 256. Times 3. 768. Cosine squared theta, sine squared theta, sine to the 4th of phi. Dotted with 16 sine of phi. For sake of room, I'm just going to write it as S1. dA. $16 times negative 768. We have 12,288. Zero to 2 pi, 0 to pi over 6. Right, the first two components are going to be 0. So when you do the dot product, those terms are 0. That's nice. So it's just this times sine of phi cosine of phi. Right, because that's what S1 is. The z component's cosine phi. Bless you. Oh boy. The Z component of S1. Remember, S1 is cosine theta sine phi, cosine phi. And we're doing the dot product. Well, the d phi part's easy. So I might as well just do that now. It's going to be 1/6 sine to the 6th phi, evaluated from 0 to pi over 6. Well, sine at 0 is 0, so it's just going to be sine of pi over 6 raised to the 6th power. And then divide that by 6. What is sine of pi over 6? It's 1/2, isn't it? Oh, that's nice. And then 1/2 to the 6th power is what, 1 over 64? What does this simplify to? I'm too lazy to open up my calculator. I don't feel like doing that in my head. Whatever, it's going to be negative. What was it? Exactly?
Yeah.
Oh, that is so nice. I love when numbers work out.
Again, how you did the DFC.
Just change a variable. Let u be sine d u is cosine. So it's essentially just u to the 5th du, which is 1/6 u to the 6th. And then just evaluate sine to the 6th, pi over 6, and 0, right? Add 0 to 0, which is nice. So it's just a half to the 6th power, which is 1 over 64. And then don't forget that 1/6. The easiest way to tackle this is to use reduction identities on both cosine and sine. Each one's going to have a 1/2. So just go ahead and factor out a 1/4. Oh my God, look how awesome that is. Reduction again. Oops. A 1 minus 1 plus cosine of 4 theta all over 2. Yes, I've already acknowledged this alert. You can stop giving it to me. 1 minus a half is a half. Then plus a half cosine of 4 theta. What is the period cosine of 4 theta? Isn't 0 to 2 pi 4 full periods of cosine of 4 theta? That just integrates out to 0. Integral of 1/2 from 0 to 2 pi is just pi. So you're left with negative 8 pi. Integral of 1/2 from 0 to 2 pi is a half times 2 pi, which is just pi. I still hold that the actual circulation integral itself would have been easier, but that leaves more. Oh, I'm sorry, 2 more. I actually had 5 for the divergence theorem. Okay. Outward flux. And again, take a look at the surface. It is the sphere of radius A, which is a closed surface. Divergence theorem applies. Divergence 3x squared plus 3y squared plus 3z squared. So the solid that our surface encloses the sphere of radius A. That has an easy description. Outward flux would be this surface integral, which according to divergence theorem is going to be this. Integrating with respect to theta just gives us 2 pi. Just going to go ahead and factor out that 3. Be left with rho to the 4th sine phi. Integrate with respect to rho, you're going to get 1/5 a. So we'll have 6/5 a pi. Integral from 0 to pi of just sine phi. And that is an integral I said happens a lot. That integral is 2. I'm sorry, that should not be a. That should be a to the 5th because it was rho to the 5th. And so there's the outward flux.
With 6 pi out in front, with the. I sure things down.
Good.
Yeah. You would have that.
This one was actually supposed to be the one that was next, but I'm glad I'm saving it for last. Nobody saw that. Going to calculate outward flux across the surface of the wedge cut from the first octant by the plane y plus z equals 4, and the elliptical cylinder 4x squared plus y squared equals 16. I'm going to go ahead and include those 3 planes because I'm dealing with the first octant. goes from 0, let's just go 5. I'm gonna leave that alone for right now. On that and plot legends. Expressions. That view doesn't really tell us much. At a really good angle. I had it. Somewhat like this. There it is. Okay. This in here's the wedge. So our surface is the surface of that wedge. Right, so it'll be right. So you have to imagine now that I'm gonna have to make that red like transparent. Right, because the surface is actually what's under. Yeah, the surface is actually what's under that. So it's this purple that's under the red, the top of the red, and then the planes, the 3 planes. That is our surface. And that red is the 4th one. One, 2, 3. That should help. Little bit, yep. So we have to ask ourselves, is that a closed surface?
Again.
This wedge. No, it's everything, right? So it's tough to see because I can't rotate that. So it's what's under the red here. This red bit is the top of the wedge. Right, and then the three planes over that bit serve as the other sides. And so you have to kind of imagine this wedge goes all the way down, right? So you know what a wedge looks like. Kind of like that, right? So all of this acts as a side, what's under the red. So it looks purple now. That acts as a side. That's why I made the red transparent. So this little bit here, it's red, but it's also transparent. So it's kind of going with the green. So that top is, so that bit of red inside is the top of the wedge. And then the three planes, right? So this would act as one of the sides of the wedge. This will act as another side. And then what's on the bottom acts as the final side. So is that closed? It is. So we can use divergence theorem. Otherwise, right, you'd have to do how many surfaces was that? 1, 2, 3, 4, 5. It's 5 surfaces. Right, you have the 3 planes. Then you have that 4th plane, the red, and then you have the cylinder. So instead of trying to describe 5 of those 5 surfaces, we just have to describe now the entire solid. First, let's calculate the divergence. Two z minus x minus 2z. Oh, that's nice. Divergence just negative x. Now we have to describe the actual wedge. Oh boy. Rectangular, cylindrical, or spherical. Believe it or not, rectangular is your best option here. Spherical is clearly a no-go. You would think cylindrical because of the elliptical cylinder. Problem with that is R depends on theta. You have to try and write You have to find bounds for R that are dependent on theta, and that is kind of a pain. Z is going to go from 0. And so this bit here coming out at us is Z. So it goes from 0 up to the red plane. Or minus Y. Y goes from 0. The square root of 16 minus 4x squared. Right, so this bit here is Y. And you can see it goes from 0 to the cylinder. Which means X goes from 0 to 2. Right, 0 to 2. You could have also tried to describe X in terms of Y. It just would have given you a fraction, which is why I didn't do it that way. Outer integral would be 0 to 2. Middle integral. 0 to the square root 16 minus 4x squared. Innermost integral will be 0 to 4 minus y. Bless you. Of just negative x dz dy dx. I'm going to get rid of that negative by flipping this order. xy minus 4x. That first integral, xy, right? It's going to be xy squared over 2. Evaluate that from 0 to the square root. It'll be that, right? I'm now going to distribute that 1/2 x through. So 8x minus 2x cubed is what you're left with. And then just minus 4x times that square root. 4x squared from 0 to 2 is 4 times 4, 16. Minus a half x to the 4th from 0 to 2 would be a half of 16. It's actually going to now be a plus. Eight x is the derivative. So I'm going to need a 1/2 times 2/3. 16 minus 4x squared to the 3/2. 0 to 2. At 2, that's just 0. That is 8. 16 minus 8 is 8. Minus 1/3. 16 to the 3/2. Sixteen to the 3/2 is 64. And that should be negative 40 over 3. So even the integral in rectangular was fairly simple. So not only was the description the easiest, but the integration itself wasn't too difficult in rectangular, which is nice.